giving me this opportunity to visit Newton Institute, and also for asking me to give this talk. So I shall talk about some work I've done recently in trying to understand supersymmetry constraints on the R34 multiplet in type 2B on P2. So I'll tell you why I want to look at this specific problem. So basically I'll begin with some introduction and motivation, and I'll tell you why I want to look at this problem. Then I'll tell you a little bit about the field content of this theory, the massless modes, because I want to construct the effective action. Then I'll derive some equations for you and show how to solve for some of the couplings. So, so the motivation is essentially very simple. You want to understand the effective action of string theory. So essentially you want to write down a low energy effective action having only the massless modes, which captures the degrees of freedom of string theory and also all the interactions. So essentially what you want to do is you want to compute scattering amplitudes, namely S matrix elements, and this will give you terms in the effective action. The vertices in effective action will directly tell you certain scattering amplitudes in string theory. In general, this is a very difficult exercise. Neither can you compute the effective action using space-time methods directly, nor can you calculate scattering amplitudes more or less anything beyond one loop. So, and also, I mean, even when you compactify on generic backgrounds, it gets even more complicated. So in general, this is a very hard problem to solve. So what I shall tell you is about, in certain very specific cases, certain couplings can be calculated. There's a very small amount of work you can do, but I'll tell you how to do that. So essentially what I want to compute is the effective action of string theory. And the effective action, which I told you, will have interactions which actually encodes vertices and hence S matrix elements in the, so they encode the string S matrix elements. So string amplitudes, and of course when I mean string amplitudes, they also have multi-loop amplitudes. So of course inside the loops you have massless as well as massless modes, massive modes propagating in string theory, also massless modes because I mean you have a conformal theory, so all the modes are running in the loops. So unfortunately these effective action also have IR divergences. Okay, so that you have to live with. But the good news is these effective action also are duality invariant. And so I'll be using duality and also supersymmetry very strongly in my talk to constrain some of these effective interactions. Okay, so that is where I'll begin. So, as I told you, this is very difficult to calculate in general. It is actually, one can calculate only some of these terms, certain BPS protected operators in certain theories. So one will be maximally supersymmetric theories, which I'll be looking at. So namely, this will be type 2A or type 2B on various tori. So of course, in my case, it will be on P2. So I'm in an 8-dimensional theory. So this is a theory where certain half BPS interactions, for example, and also quarter and 1/8 BPS interactions can be calculated. And I'll look at only the half BPS sector today. Okay. Of course, another class of theories where you can write down certain interactions, which is namely the 4-dimensional string theories with 8 supercharges n equals 2. That is possible essentially because I mean a lot of these homogeneous amplitudes can be calculated directly using the topological string theory, essentially because of the world sheet supersymmetry and also because of the power of special geometry. But there's another class of examples which I won't talk about today. So so let me begin. So essentially the genesis for what I'm going to tell you began with the calculations in 10 dimensions, essentially by papers, in papers by Green and Gutperl, and also in later papers by Van Hove and Sethi. So this is the origin of this whole subject essentially, and I'll tell you how to generalize this to what they did in lower dimensions. So basically I'll be looking at theories with maximal supersymmetry, and it will be also maximal supergravity because you have gravity, and the scalars parameterize a coset space G mod H. So this is global. This is something non-compact, and H is maximal compact subgroup. And so you can directly start from D equals 10 dimensions, where this coset space is SL2R mod U1, and go down all the way, for example, to D equals 3, where you have E88R modded out by SO16. And we can also go down to lower dimension, but then it becomes infinite dimensional. And of course, here in D equals 9, you have exactly the same structure tensored with R plus, which is actually the volume of the circle. And in D equals 8 is the case I'll be looking at. So now you understand why I'm looking at D equals 8, because I'll review a little bit about what's known in D equals 10. There's the simplest case. This is the most complicated case. And this is kind of not that complicated because all you're adding is a volume factor. And this is the next kind of difficult case to look at. And this is why I'll look at this. And here the modular space is SL2R mod U1 tensored with SL3R mod SO3. And of course, this is the only case where the modular space is factorizable, is reducible, and this actually adds to some additional complications. So this is the motivation for doing this. And of course, we know in string theory, due to non-perturbative effects, this continuous symmetries are broken, and you have some duality, which is called U-duality, which includes all dualities, for example, S-duality, T-duality, and so on. So in this case, the U-duality group is thus conjectured by Hull, Townsend, also by Whitman. SL2Z, here it's SL2Z tensored with SL3Z. And of course, this gets more and more complicated, and here you get complicated duality groups like E77Z, which is also, so far as I know, not very well understood in mathematics. But for today, we'll just stick to something simple. In particular, we'll mostly stick to this because this will illustrate the general features without getting into too much complications. Okay. So first, let me review what is known in 10 dimensions, just to set the tone for why I want to look at R to the 4 couplings. So in 10 dimensions, I essentially want to write down the effective action. So of course, at leading order, I'll have the Einstein-Hilbert term. And the question is, what are the corrections? Because of the enormous amount of supersymmetry, this is in 10-dimensional flat space, so 32 supersymmetries, so the R square and R cube terms vanish. So the first correction here is R to the 4. So this is at the 2 derivative order, and next correction turns out to be at the 8 derivative order. Then the next terms turn out to be D to the 4, R to the 4, D to the 6, R to the 4, and dot dot dot. So these are supposed to be the BPS protected terms. Okay? And of course, in 10-dimensional type 2B string theory, there's a complex scalar tau, which actually transforms in the following way under this SL2Z, A tau plus B by C tau plus D. So the question is, what happens to these couplings? Because these are generally functions of tau and tau bar. Of course, this is at the supergravity level, so this is just one. There's no renormalization here. And these are actually couplings. Let me call it some F1 tau of tau bar. This is some F2 tau tau bar, and this is F3 tau tau bar. So the question is, what are F1, F2, and F3?
Sorry, so what's the statement about powers of R higher than 4? That they are not protected, they're
R to the 5 and stuff like that.
6,
yeah. No one knows. No one knows.
Okay.
Yeah.
But they are of the same order in
yes, exactly. For example, R to the 7 will be of this order. So it's known that there are some certain kind of couplings. In fact, when you lift to M theory, it's believed that after R to the 4, the R to the 7 is the next coupling which is non-vanishing. This one, when you lift to 11-dimensional, this actually vanishes. But no one knows, of course, if this is the same supermultiplet, for example. Actually, this I won't talk about, but it's only known in linearized superspace how to construct this term. Anything beyond that even is not known how to construct in superspace. So it's very little is known, actually, you'll realize. But this I'll quickly go through because I want to tell you what the answers are for F1, F2, and F3, okay? Because this is just the introduction for the 10-dimensional case, and this is the kind of the work which started with what Green and Gutperl did. So I'll just tell you the answers, okay? So for that also I'll write down some formula which will also be needed later because I'll also have an SL2Z coming up later, okay? So I'll introduce what are called the non-holomorphic Eisenstein series. And these actually are invariant under tau going to A tau plus B by C tau plus D, but they're non-holomorphic in the sense that they are functions only of tau and tau bar. Okay, and they are defined in the following way: ES tau tau bar. The factors are not relevant, okay, so I'll just put a proportional sign here. It has a zeta function of 2s. Tau is imaginary part of tau to the s, plus then there's a zeta function of 2s minus 1, tau 2 to the 1 minus s, plus there's other kind of terms which involve root tau 2, and this sum here. So you have a sum over the integer lattice, but removing the origin so that it's well defined. So this is the Bessel function, okay. So this is the whole expansion. up to various numerical factors of 2s and pi's and whatnot. So the important thing is, here in type 2b in 10 dimensions, tau 2 is 1 by g string. So this is basically the large, this is the last tau 2 expansion when you actually do a Poisson summation, and I must tell you what the complicated but very simple looking actually expansion is. This expansion is the following. This is just given by tau 2 to the s by m plus m tau to the 2s, and you have this lattice sum where the origin is left out, okay? And here write it as an integral representation, do a Poisson summation, and this pops out in the last tau 2 limit. So in other words, in the weak coupling theory, perturbative string theory, you get only 2 power behave terms and other terms which are exponentially suppressed. In particular, for large tau 2, this goes as e to the minus 2 pi m n tau 2. So immediately see in type 2b a flat space time, this is only 2 perturbative contributions, and this is actually the action of a d instanton or an anti-instanton depending on whether mn is positive or negative, right? And it turns out that these couplings here are related to this Eisenstein series. So let me just give you the answer. So F1 tau tau bar turns out to be E3 halves tau tau bar, okay? And this has 2 perturbative contributions, essentially only at tree level and at one loop, and this is proportional to zeta function of 3, proportional to zeta function of 2. And when you actually do this scattering amplitude calculations in string theory, this is exactly what you reproduce. So it also matches with the worldsheet perspective, okay? So next, let me tell you what F2 tau tau bar is. That turns out to be E5 halves tau tau bar, and this turns out to have only 2 loop amplitudes. This is 3 level and another is 2 loop, okay? So it's again, and this is proportional to zeta 5 and zeta 4, and this has also been checked actually by de Hocker, Fong and Gutperl, so that this is also correct and the normalizations also match precisely. But actually beyond that very little has been checked, and the question is what is the answer for F3? Here's a little bit more complicated, and I must tell you one more property of this Eisenstein series. These Eisenstein series satisfy the Laplace equation on moduli space, so on the fundamental domain of SL2Z. So in other words, 4 tau 2 square d2 d tau bar es.
Can I
just 1 second. Yes.
You said that had been checked, but you were telling us earlier that in fact after the out of the fourth, the next term that appears is after the seventh.
Oh no. See, these amplitudes certainly exist. This in 10 dimensions. This in 10 dimensions.
Yeah, we're in 10 dimensions.
Yeah, we're in 10 dimensions.
After the seventh was the net pure R power.
I see.
Not the next term.
I see.
No, even
these D's
yeah.
on R.
well, even a 5 graviton amplitude has been checked.
Ah.
But the point is, it's not known whether they actually have such nice renormalization properties or not. Essentially, the simple thing is what you actually do is essentially you just take the 4 graviton amplitude on the 3 level, that's on the sphere, and do just essentially this calculation. Okay, this is what you do, and you basically get it as a power series expansion in alpha prime, and then basically the first term is r to the 4, and this is d to the 4, d to the 6, and so on. So these are the terms you know for sure actually exist. In fact, this is just given by the Virasoro-Shapiro amplitude. So if st or the Mandelstam variable, this is basically minus by very simply 1 plus u, and r to the 4 and e to the minus 2 from the fact that it's on the sphere. So when you expand, so leading order, this first term turns out to be zeta 3 times r to the 4. Then the first subleading term turns out to be zeta 5 times s square plus t square plus u square acting on r to the 4 and so on. So that is how you know the existence of these terms. And then you can of course also do the 1 loop and the 2 loop amplitudes, and these actually have been checked. And this 2 loop, the 1 loop amplitude actually vanishes here, and the 2 loop amplitude precisely gives this. So the question is, what is F3 tau tau bar? So it turns out that these non-holomorphic Eisenstein series satisfy Laplace equation in moduli space. Okay, so correspondingly, these two couplings also satisfy Laplace equation. But this one does not satisfy Laplace equation anymore, it satisfies the Poisson equation. And the Poisson equation, the coefficient for the Poisson equation is given by the coefficient of this term. Namely, F3 tau tau bar satisfies this equation. The Laplacian acting on F3 is given by 12 F3 minus 6 E3 half square. Now why this comes out, I'll tell you, it's a consequence of actually supersymmetry that you can easily see without doing any calculation, and this was proved by myself and Seti some time ago. Okay, so essentially this is all that I wanted to tell you about in 10 dimensions. I mean, certain more things are known, but that's all that we'll need for today. So now I'll focus on the case of d equals 8. Okay, the next simplest case, and let's see how far we can go.
So sorry, this what's it, F3?
Yeah.
Ignoring the last term, it satisfies
Yes.
the E4, the equation
Exactly.
for E4.
Exactly.
is it?
Exactly.
Okay, and
Exactly.
why is that? Just so.
Sorry, why is it? Yeah, exactly.
You
Exactly.
don't- I mean, just because it is.
Exactly. And then it's absolutely crucial that it's 12 and nothing. I mean, this one is a fake. I could have rescaled F3. But this is absolutely crucial. It's 12. So because I mean, actually it turns out that this resist contribution is only up to genus 3, okay? And the genus 3 amplitude cannot be determined for exactly the same reason, because the genus 3 amplitude goes as 1 by tau 2 cubed here, okay? And this will actually give you -3 times -4 here when you act with the Laplacian, which cancels this. So the genus 3 amplitude actually is not very easy to calculate from here. So you have to use some unfolding techniques and stuff to calculate it. But it's absolutely crucial, this number is 12 and nothing else here. Yeah. So now we're in d equals 8, okay? So first let me tell you a little bit about the massless modes of the theory. In other words, what are the degrees of freedom in effective action? So first the bosonic degrees of freedom. Okay, of course you have the metric. And this I'll explain. This is 3 by 3 matrix LMI, 2 by 2 matrix L capital U small u. And let me write down the field content first. Okay. So this is the metric. So this is a 3 by 3 matrix which satisfies determinant LMI equals 1. And I'll show you this contains the degrees of freedom of SL3R mod SL3. This will be clear later, but they actually capture the five moduli. This is in the 3 of SL3. This is in the 3 of SO3. Okay, and similarly, this again satisfies determinant of LU small u is 1, and they capture the degrees of freedom of SL2R mod SO2. This is again in the 2 of SL2. This is in the 2 of SO2. And so these are 6 abelian gauge fields in the 3 of SL3 times the 2 of SL2. 2 forms in the 3 of SL3 uncharged under SL2. And for this one, you define the 4 form, which is dc plus Chern-Simons kind of terms, such that you take this F4 and you take the derivative of the Lagrangian with respect to F4 and you define it to be G4. Then actually F4 cell dual, anti-cell dual, and G4 cell dual, anti-cell dual forms a 2 of SL2. This is just like electromagnetic duality in 4 dimensions. So immediately see that SL2 is a symmetry of the equations of motion, not a symmetry of the action. But SL3 is a symmetry of the equations of motion. Sorry, SL3 is a symmetry of the action also. And this SL3 times SL2 actually is a nice interpretation from M theory, because the SL3 becomes a symmetry of the large diffeomorphisms of the T3, and SL2 is a diffeomorphisms of the complex structure of the torus. Okay, so this is the field content so far the bosons are concerned. Now let me tell you about the fermions. Now the fermions here actually, as Kugo and Townsend showed many years ago, these are basically this symplectic Majorana fermions. But let me just tell you what my convention is going to be, because I'll be using this fermions convention all the way. So for the left movers, I'll have, of course, so these will be charged only under U1 and SO3, just like in GR where they're charged under H and not under G. So I must tell you what the charges are. So the left moving, so this is a symbol of course for left, and there's an A index here. Let me write it down. These are the fermions here. So this is in the 2 of SU2. This is in the 2 of SU2. This is in the spin 3/2 of SU2 because they also, this satisfies the extra constraint that this is equal to 0. Okay? And so I've told you the SU2 charges. Now the U1 charges. Now the U1 charges are +12, +3/2, and -12. Okay? And for the right movers, again, it's the same representation of SU2. The U1 charges actually are, of course, the opposite sign. And for any fermion, psi right is given by sigma 2 psi left star, where sigma 2 is basically the sigma matrix, the second component of sigma matrix here. Okay, good. So this is so far as the field content is concerned. Now what I want to do is actually to make contact with the field content of type 2B string theory on T2, because right now this is a little bit more abstract, and I want to really see how these moduli are encoded in the geometry of the T2. Okay. So, so I'm looking at type 2B on T2, and the scalars are the following. So I get tau, which was of course there in 10 dimensions. There is this scalar modulus on the 2 torus, which is given by Bn plus Iv. So this is the volume of the 2 torus in the string frame. This is the expectation value of the Navier-Stokes 2 form on the torus, and so and then basically I have this expectation value of the Ramon 2 form on the 2 torus, and of course so 1, 2, 3, 4, 5. That's it. That's what you have. Okay. And it turns out, of course, this gives an SL2Z in string theory, SL2Z tau of S duality. This gives the SL2Z T of T duality. Okay, and these actually are all included in the SL3Z. I'll call it M of the U duality group. And apart from that, of course, there's a complex structure of the torus U, which actually characterizes the SL2ZU. So this is the SL2 times the SL3. Okay, so the T duality as well as the SL2Z tau, strong coupling S duality, are all part of the SL3, and the diffeomorphism of the complex structure of the torus is given by the SL2. And now I want to see how these moduli are encoded in this matrices L, because I want to write down those matrices in terms of this physical coordinates on moduli space. Okay, so for that, I'll have to use a very well-known theorem called the Iwasawa decomposition, which tells me the following. For this case, I can write down L as H, K, N, where this is the matrix of gauge transformations. Okay, this is a matrix with only diagonal entries and with determinant equal to 1. And this is actually an upper triangular matrix with diagonal elements equal to 1. This is a theorem, and an important thing is, when I'm working a fixed gauge, I can just set H to 1 and calculate L. In other words, if I want to go from that gauge to another gauge, all I have to do is multiply by an appropriate H on the left, which is either SO2 or SO3, depending on which case you are. So first let me tell you how it works for SL2 mod U1. Okay, it's an exercise which is actually not very difficult to do. So in this case, this matrix LU turns out to have set H equal to 1. Turns out to be the following. There is a root U2 1 by root U2 0 0. This is K, and for N it turns out to be 1 1 minus U1 by U2 0. Okay. And for that, for example, when you actually calculate the action actually has the standard form. This is d mu U star by du2 square, for example. This is the terminal Lagrangian. Okay. I mean, I can go into details if you want me to, but this is essentially what happens at the end. So it gets a little more complicated for SL3 R mod SO3. I'll just write down the answer here. And again, you can calculate this action analogous to that, and this is exactly what matches what was obtained by Kritzis and Piolin some years ago, up to some field determination. So here basically again is very simple. So and it turns out I'll define this quantity nu inverse is tau 2 v square. Okay, this is the volume, and this turns out to be mu to the 1/3 tau 2 here by root tau 2 0 here, and this turns out to be 1 1 1. Real part of B, and this is nu by tau 2, the imaginary part of B, where B is defined to be BR plus tau BN. So this is it. So now explicitly see in a choice of fixed gauge how all the 7 moduli of the compactification are encoded in this L matrices. Okay? So now we are ready to proceed with the calculation of this S matrix elements. Okay? Okay, so what I want to do is, of course, as I told you, after R, the first correction is R to the 4. In other words, that's 8 derivatives. So it is in the same supermultiplet as 16 fermion terms. So I want to look at certain 16 fermion terms in the effective action. Of course, because it's extended supersymmetry, the bad news is, of course, there's no official formalism, but for the certain class of terms which I'll be looking at, it's enough to have an on-shell linearized formalism. So let me tell you what that superspace is, okay? So I want to construct superactions. So what I'm telling you right now is largely due to the work of Siegel and Berkowitz. Okay, so I'll have to look at two kinds of superfields. One is a chiral superfield, another is a linear superfield, okay? So first let me define for the chiral superfield. This is the more or less easy one. This is the superfield W, which is uncharged under SU2, and it carries U1 charge plus 2, okay? And if I define supercovariant derivatives, superderivatives, excuse me, dl is equal to, in a standard way, mu d mu, and of course this satisfies dr of w equal to 0 and dl bar and dl of w bar equals in a standard way. In other words, it's a function of theta and not theta bar. Okay, so this is the chiral superfield, and now let me look at the linear superfield. Very in 8 dimensions. Yes, yes. So d equals 8. So that was the chiral superfield. Now let's look at the linear superfield. So you can think of it a little bit analogous to the construction of superspace in 4 dimensions. You can think of the chiral one as the vector multiplet moduli, and the linear ones are actually the hypermultiplet moduli. So, but surprisingly, for the linear multiplet, things are much more complicated. So for the linear superfield, okay, this is defined as L, A, B, C, D. Of course, H is in the spin half of SU2, and it's completely symmetric. So this is actually in the spin 2 of SU2, and under U1 it carries actually charge 0. Okay, this actually and it satisfies another constraint, which is dl A B C D E equal to 0, and similarly also for dl or R. Okay, this is a constraint. And of course, this cannot be completely correct, because I told you there's a chiral superfield, and I told you there's a linear superfield, but typically in theories with maximal supersymmetry, there's only one multiplet and not two. So it turns out there's a relationship, a very complicated relationship between the linear and the chiral multiplet, and it actually is the on-shell relation for the supergravity fields. I'll just write down the relation. This is actually which makes them go on-shell. It turns out that essentially dl gamma mu mu dl of w turns out to be dr L. So if you want to have indices, this is some AB, this is some AB, CD, CP. That's the relationship. Okay. So now, what are the degrees of freedom in W and L? Let me just write it down. So because these are the things which we'll use in constructing a superaction. Okay. So W, actually the leading term turns out to be just is basically U2 in a gauge fixed version. In other words, this W depends only on the to leading order. It depends only on the SL2 moduli, and not the SL3 moduli. Okay, so it's U2, and the next term, of course, is just given by theta bar lambda, because that is the supervariation of this. Okay, plus other terms. This won't be relevant right now, but I might come back to them later. And so this is what W looks like. And now the question is, what about L? So L, we want to choose a simpler notation, so that they characterize the SL3 moduli, and I'll actually define this superfield, which is given by this. So this is symmetric and traceless, okay? But in other words, it's still in the spin 2, but I want to write it in the vector representation. So that is actually given by this, and is symmetrized traceless ABCD. And so for this Lij, let me write down to leading orders in theta what happens. This is of course this is a real superfield, so it's a function of theta L and theta bar, theta R. So to leading order it's Lij. This actually includes in a complicated way the various components depend on the 5 modular of SL3 mod SO3. And to the next order you have a of course you have a theta bar R, which turns out to be sigma I chi JL plus sigma I. So it involves the chi fermions. Okay. In other words, when we actually expand the superaction, this will give us contributions to the chiral superfields, and this will give us contributions to linear superfield, and this will capture the degrees of freedom of SL2. This will capture the degrees of freedom of SL3. Okay. So now we can construct the superaction. So for the chiral superfield, let me write down the superaction. So the Lagrangian is given by an integral over only the theta L part of the superspace because it's chiral, and an arbitrary function of W. That's so surprising. And let me define what d16 theta bar R is a unique Lorentzian invariant which you can have. So you have d theta bar R, there are 8 of them. Alpha 8. Remember these are chiral fermions of 8 dimensions. So this is an epsilon alpha 1 to alpha 8, beta 1 to beta 8. There's an A1 to A8 for the SU2, B1 to B8, epsilon A1 B1, all the way up to epsilon A8 B8. Right? So this is a measure in the Brazilian part of the integral. Okay, so this is the integral. This is the superspace action for the chiral superfield. Now let me tell you the action for the linear superfield, and here it's not so simple. So here I'll tell you essentially what Berkowitz did in writing down this action, but of course I'll write it down covariantly. He did not.
It's linearized, right?
Yes.
Equationally, yeah.
Yes.
Yeah.
Yes. Yeah. No one knows how to go beyond nonlinear, even in 10 dimensions. So now for the linear superfield, there's a nice trick. So the point is the following. So remember I wrote down superfield as L, A, B, C, D. This one 1 and 2. So I'll write a plus in this. In other words, V plus will be V1 plus I, V2. It's easier in that basis. So take this combination of the superfield, I'll call it L twiddle, and only this combination, nothing else works. So one with all plus, and like a binomial expansion essentially. So it's xi is a parameter, minus. So it's 1, 4, 6, this thing. And from the various properties of this, what you can show something is very nice. If you actually take d minus of L, the minus 1, of any function of GL twiddle, it turns out to be minus psi d plus of L GL twiddle. So a minus and a plus can be converted. And similarly, d minus R GL twiddle turns out to be minus d plus R GL twiddle. And this is absolutely crucial that the superspace here is actually a function. The superfield is a function. I mean this integral which I'll have here will involve integrals only over L twiddle. So let me write down the superaction now. Okay. The superaction is given by this d8 theta bar R, d8 theta bar L. I'll have an arbitrary function of GL twiddle, and of course this is also a function of this parameter zeta. Then at the end I'll just integrate over d zeta about 0. Okay, plus its summation conjugate. So now, where of course this actually is defined in analogous the same way, you have for the 8 of these you have alpha 8. For the right movers you have this, again the same epsilons, this is A1 to A8, B1 to B8, epsilon A1, B1, all the way up to epsilon A8, B8. So, but the important thing is because of these constraints, and this is a function of only L twiddle, that it turns out to be this turns out invariant and supersymmetry. Essentially, because you see, roughly speaking, this is 8 powers of dl and 8 powers of dr, right? But whether it's plus or minus doesn't matter because everything is a function of only L twiddle. So you actually can have all minuses here and all minuses here, for example. And now when you make a super variation of this guy, you either pick up a dl or a dr. But again, because it's acting on only L twiddle, you can interchange pluses and minus. So you're always going to have 9 powers of the same guy, which vanishes because there are only 8 of them in kernel superspace. This is actually super invariant. Okay. Now this plus this Hermitian conjugate, I'll just call simply as a function of Lij, and thus for this guy, I get the super action d8 theta bar r, d8 theta bar L, some function of the SL3 moduli. So that's it. Now we are set because I have an action for the SL2 moduli, I have an action for the SL3 moduli. I have to just look at 16 fermion terms in these interactions. Okay. So now let's do it. Okay. So first, let us look at the SL2 mod SL2 moduli. So actually at the order theta level in W there was a lambda term. So when I actually have integral over 16 thetas, I actually get a lambda to the 16th term already. There are other ones related by supersymmetry, just by expansion of that. I'll just write down the answer. And so essentially, why do we want to look at 16 fermion terms? Because the philosophy we want to follow is the following. We just know that 0 is the super variation of the action up to total derivative terms here. And I want to expand the supersymmetry transformations as delta 0. This is the supergravity supersymmetry transformations. And the next I'll just call delta 3 because this is r, then the next is r to the 4. So the r square and r cubed are left out. Okay? Plus dot dot dot. And the action similarly, as 0 is a supergravity action, next is the r to the 4th term, and so on. And this is the whole action basically. Okay. Now when you expand here to leading order, you get delta 0 is 0 equal to 0, which is of course the fact that the supergravity action is invariant under the supergravity supersymmetry transformations. The next term which you get is delta 0 S3 plus delta 3 S0 is equal to 0. This is what we will be using. Okay. And in other words, we need to construct certain terms in the r to the 4th supermultiplet and see what they vary into under the action of supergravity supersymmetry transformations. And here, after some thought, I mean, the frustrating part is you don't know what S3 is, you don't know what delta 3 is, but for our purposes, you can still see there are only very few terms which will actually calculate, which contribute, and you can actually explicitly calculate it. That is what I'll do. So in S3, I'll just write down L3 here. Okay, E inverse L3. Let's write down certain terms which are relevant for our purposes. And you'll immediately be clear why. So one is 16 fermion term of lambda L. This is a function of only UU bar because it depends only on the chiral superfield. This depends on 16 fermions also. And this is some, I'll call it F2 UU bar plus dot dot dot. Okay. And right now it won't be obvious, but I'll just write down some numbers here. I'll call it F12 minus 12 and I'll call it F11 minus 11. It's essentially half of the U1 charge of this guy here, the minus of half of the U1 charge. This actually has U1 charge 24. So this is 12 minus 12 is the half of that. This actually is U1 charge 22. This is half of that. And these numbers will become significant a little bit later. But right now these are some numbers which are function, and these are moduli functions of UU bar. So the question is, can we fix those? Okay. And it's not obvious at all, but after you do the calculation, you actually see that even if you don't know what L3 is, only these two terms are good enough for our purposes. So why is that true? So first let's try to look at delta 0 of L3 and see what we get. So first let me look at delta 0, which actually varies into the following. So this is a psi r, okay? Psi r lambda L to the 15, lambda L to the 16, epsilon L. Okay? And actually you can see the super variation of that gives you something like that, because delta of u actually has a lambda L of epsilon L, which actually adds to this to give you precisely this contribution, right? So for example, you can immediately see there will be a contribution coming from here. It also turns out to be contributions coming from here, which actually comes from the gauge-fixed supersymmetry transformations. And they're actually, well, I should write it here. From here actually you can see from the gravity, from the Vielbein variation you get a psi r epsilon L, so there will be a contribution from here as well as a contribution from here. But the important, absolutely crucial thing is there's no other term in the 16 fermion effective action which could have given a contribution of this kind. Just by trying to write down what are the possibilities, even you have absolutely no idea of what the whole action is. So at the end of the day, what you get is the following. Delta 0 of L3 gives E. I'll write down the answer here. This is lambda bar to the 16, epsilon bar r, gamma mu, sin r. And this turns out to be the following, D11. I'm just setting all numbers to 1, okay? F12 minus 12. Now what is D11? For that, let me go back to these guys here. So in general for SL2Z, you can define automorphic forms of non-zero weights. Such that the Eisenstein series are automorphic forms of weight 0 in the sense that they don't transform at all. Okay? So the automorphic form of weight Mn is defined in the following way. Phi of weight Mn tau bar under SL2Z transformations transform in the following way. So this is CD C tau plus d to the m, C tau bar plus d to the n, phi Mn tau bar. Okay? And you can define covariant derivatives on moduli space such that d of m is I tau 2 del tau minus m by 2, and its conjugate d bar of n is minus I tau 2 del tau bar plus I n by 2. And these are the very nice properties that dm acting on phi mn takes you to phi m plus 1 n minus 1. Okay? And d bar n acting on phi mn takes you to phi m minus 1 phi m plus 1. In other words, dm acting on phi mn increases this and decreases this, and d bar n increases this and decreases this. And these are modular covariant derivatives. And now actually you can see these from hindsight. Now you can actually see that these, the reason for writing 11 minus 11 and 12 minus 12 is the following, that these are automorphic forms of non-trivial weights. In other words, these are modular forms of weight 11, modular forms of weight 12, and no wonder you get precisely the D11 coming out of it from the exact calculations. Okay, so D11 of F11 actually is proportional to F12. And it turns out, when you try to write down terms in the effective action at the supergravity level, 4 fermion terms, there's absolutely no 4 fermion term which under any possible delta 3 could have given you this kind of a contribution. That you have to check. In other words, you immediately get an equation that D11 F11 minus 11 F12 minus 12 is equal to 0. So in spite of the complexity, things at the end are very simple. So let's try to look at another super variation. So we did the super variation such that we got the derivative of this guy, right? Now let's try to get the derivative of this guy coming into the picture. In other words, now we want to look at another super variation.
Why can't the variation of the first order action give you anything to
Yes,
do?
because if you try to write down all 4 fermion terms in the first order action, like lambda L square, lambda R square. For example, you see, essentially I've given this kind of, you have to check a little bit. For example, you could have had a term like lambda L square, lambda R square, but that couldn't vary because you'll have at least 1 lambda R left, for example. You have to write down all possible terms, and it turns out there's no other term. So that's the reason this one doesn't contribute here. Okay. So now let me look at the other super variation, where I want to see the variation of this guy here. So I want now the things to vary into lambda L to the 16, lambda R epsilon R, and that's clear will work because the delta U bar will actually has a lambda R epsilon R, so that will give this. So in other words, I'll get a contribution from here, and here clearly the only contribution will be from the gravity now, because at the end I don't want any gravity now. That can be calculated also. And again, what you get is delta L3 turns out to be E, and it turns out to be d bar minus 12, f12 minus 12 plus f11 minus 11 times what I had here, so it's epsilon bar L lambda r lambda L to the 16. Okay, but now in this case it turns out that is actually a 4 fermion term in S0 which could have varied here. Okay, in fact this is precisely the term of this kind, because you see now actually if you have a delta 3 of lambda r which goes as lambda L to the 14 epsilon r, a variation could have given that, right? In other words, this is a case where S0 could have contributed for a certain choice of delta 3. So for that we need to know this term in effective action, and that's kind of a long calculation, but it works out nicely because what you just take is the 11-dimensional supergravity and due to Kramer-Julian Shirk, and there of course it's very simple, so the 4 fermion terms are very explicitly written down. So dimension reduced on T3, and you can get this term here. And I'll just write down the answer. So there's a term here which actually is something like, I'll not be very specific about factors, but it's roughly this. In fact, well, this is exactly this. So this is what you have. And now I want to have a super variation of this kind, which will precisely give me this kind of a contribution. Okay. But so now let's see what are the possibilities. From now on, these are calculations which even in my calculations have not worked out completely, because I wanted to get the structure coming out. There are many possibilities, but the structure from supersymmetry turns out to be easily determined, apart from factors which can be calculated otherwise. So I'll just tell you roughly schematically how to get this. So what I want is a supervariation, corrected supervariation of lambda r of this kind, which actually produces this kind of a supervariation in the final answer. Right? You have to play around a little bit, and one possibility which works is the following. I'll tell you why it's also nice. So delta 3 of lambda r, some alpha in A index, turns out to be, and I want it to be proportional to lambda L to the 14 times an epsilon. Remember, I want it proportional to lambda L to the 14 times an epsilon r. So I just put in a beta gamma here, so an AB here, and this is G1 function of u bar. Gamma alpha, this is some beta b. Okay, this works. Immediately this also works, plus there's something else that also works. So this is beta gamma. So this is an answer. Okay, this is all lambda L to the 14. There's an epsilon r here, and what really works is that when you plug it in, this gives a contribution of this kind. So let me write down the answer. So this gives that delta 3 of L0 gives E, some G I'll define momentarily, lambda L to the 16, epsilon bar L lambda R, where G is basically G1 minus 4G2 plus 6G3. This combination, G1 minus 4G2 plus 6G3. So in other words, it seems that you have not made much progress, because now actually you have this other function G here, which you don't know really what it is. But now actually I shall use the closure of supersymmetry algebra to completely fix this G and show you that exactly this combination arises. Okay, that will actually complete the full calculation immediately. Let me just write down the answer here, because the details are quite complicated. So the point is the following. I take the commutator of two supersymmetry transformations at the 0th order and calculate it on lambda r. So apart from the standard translation term, this will give an answer. This will be another kind of contributions here, which will involve d slash lambda r. In other words, this is the fact that it's on shell, so it closes up to the equation of motion. So if I calculate the next subleading order correction to this closure, what I will get is the supersymmetry transformation commutator, and one at the 0th order, next at the subleading order, right? 0, 3 lambda r plus delta 1, 3 delta 2, 0 lambda r. That I can calculate because I know what delta 3 of lambda r is. Okay, and it turns out after you do this calculation, you get exactly the same space-time structure coming out here. And what you get is exactly D11 of this G comes out with actually a lambda L to the 15. Okay? And absolutely crucial is that G turns out to be precisely the same G here, G1 minus 4, G2 plus 6, G3. So now if you plug it using the equation of motion now gives d slash lambda r plus d11g lambda L to the 15 is equal to 0, right? This is the corrected equation of motion. But we know from the action that, in other words, this must be proportional to F12 minus 12. Because remember the equation of, because the action at lambda L d slash lambda r plus lambda L to the 16. And this was the modular form of weight 12 minus 12. And solving this equation, you immediately get that G is proportional to F11 minus 11. In other words, this just changes the coefficient of this guy here. So finally, you get this equation, set of equations here, D11 of F11, F12, and D bar of minus 12, F12 minus 12 is F11 minus 11, right? So which tells you that each of them satisfy your Laplace equation in moduli space. Okay? This also proves that the r to the fourth term also satisfies the Laplace equation moduli space, and what you are left is just a fixed coefficient. Of course, this coefficient can be fixed completely using the calculations I've done, but it gets very tedious. So the coefficient, of course, you can trivially, in principle, is possible using supersymmetry. So that proves that supersymmetry fixes this completely. But it's easier to fix it using some perturbation string calculation because it's only one answer, because one coefficient. If you know the tree level amplitude, you know the answer. So that fixes it, and at least for this subset of couplings, it also proves the non-denomination theorem for that these couplings is the function of only u and u bar. In other words, in string theory, they receive contribution, and in particular, they're independent of e to the minus 2 phi hat, the string coupling at dimensions. So these couplings receive contribution only from one loop in string theory, and no other perturbative or non-perturbative contributions. So this is for the chiral superfields. So naturally, I don't have much time. So I'll just, for the linear superfields, in other words, for the SL3 model, I'll just tell you roughly what the answer is. Because it gets much more complicated actually. So this is for the SL3 moduli. Essentially, it gets complicated because L is a real superfield, so there are all kinds of terms contributing, not chiral, so that's the problem. So the analog of, remember that we actually started with two terms, right? Lambda L to the 16 and lambda L to the 15 psi r. But here there are many terms. So let me write down some of the terms which actually matter. So this is integral d8xe, and I told you about the chi. Remember the supervariation of the SL3 moduli gives this chi fermions, which are in the spin 3 halves of SU2. And you can actually construct interaction which have 8 of the left movers, 8 of the right movers. And they're actually characterized entirely by the SU2 charges. So I'll just call G16 here. And I'll look at the symmetric part, so which is the simplest one to calculate. So that is actually in the spin 32 representation of SU2. Okay? I'll just write down one of these terms to show you what they look like. And then you calculate another terms here, which is chi L to the 8, chi R to the 7, psi L. And this is in the spin 30. Another is conjugate chi R to the 8, chi L to the 7. This is also in the spin 30 and so on. Okay? So let me write down one of the terms to actually show you what the structure. I'll just write down this term to show you what the structure is. And I'll just give you the answer how this works in that case as well. So chi L to the 8, chi R to the, this was very, very schematic, but you can write down in complete Gaudy details what the expression is. You have epsilon alpha 1 to alpha 8, beta 1 to beta 8, and this actually, chi L was my shorthand for sigma I chi j L symmetrized traceless, so it's in the spin 2. So in other words, you have 8 of them, so you have some J8L, there's an alpha 1 to alpha 8, there's an A1 to A8, and for the betas, there's some sigma K1 L1 R, some beta 8, there's an B1 to B8, there's the usual epsilons, And you see I have this huge number of indices floating around here. These are actually absorbed by the G16s. The G16 which I have here. In other words, G16 carries the index I1, J1 all the way up to I8J, then K1, L1 all the way up to K8, L8. Okay, so that's if you symmetrize it's automatically symmetrized here, but if you symmetrize pairwise also, this actually gives you the spin 32 of SU2. Okay, so now one can try to do exactly the analogous trick which I did. Let me tell you the answer. So again, one can try to start with supervariations of this moduli here. In other words, get a derivative of G16 and see what it gives you. And among the set of interactions, it turns out to be quite simple, including S3 as well as S0. And schematically, D of G16 gives G15. Okay, D of G15 gives G16 plus G14. So there's nothing more to go beyond G16. So it was the possibilities were to go up by spin 2 and go up down by spin 2. So it was 17 and 15. So there was no 17, so it's 15. So when act on G15, could have gone to 16 and 14. That's all that it did. And it's very simple. So it just goes down to this. Okay, all the way up to D of G0. This is the R to the 4 interaction. G1 and so on. In other words, it's a very nice structure. If you know G0, you have to know one of them. You know what G1 is. The next one actually will involve G1, G0. That will tell you what G2 is. For example, here when you come here, you know what G14 and 13 is. You know what G15 is. So here what you know, when you know G15, you immediately know what G16 is. And this is a trivial identity. So it is a set of equations. But of course, I've been a little bit simplistic here. There are other possibilities here with possibly non-zero coefficients here, but which will always involve terms with lower SU2 spin. For example, you could have had a term like D of G14. But the important thing is always in some sense upper triangular. I mean, there's only one more and always less. Otherwise, if you start from here, if you know one of them, you can iteratively solve for the entire supermultiplet. So I'll just end with this comment and tell you what the R to the 4th term is. That will end what I'll tell you. So here actually I'll be very schematic, of course. So D of G0 gives G1 and D of G1 gives G2 plus G0. So this one had nowhere else to go down. This one went up and also went down. So finally the equation for G0 which you get is the following. This is Laplacian in the SL3 moduli space. G0 turns out to be some lambda 1 G0 plus some lambda 2 G2 Ij Ij. Okay, these are some indices here, and it turns out this is roughly the psi L to the 8, psi R to the 8 coupling, also in the same supermultiplet as R to the 4. And this one actually is something like psi L to the 7, psi R to the 7, IR chi L, and this Ij indices here are the precisely the ones which are contracted here. Because remember, each other sigma I chi, so there are 4 indices here. There's a trace of that. So this is the kind of interaction which you get. Now you see this actually no more satisfied Laplace equation, but it satisfies Poincare equation moduli space. But the important thing is the source term in the Poincare equation also given by a term in the same supermultiplet. Now of course beyond this is difficult to say because in the literature actually these are conjectured to satisfy modular forms of SL3Z of non-zero weight. So it suggests that either this is 0 or this itself being of weight 0 actually is proportional to G0. So that's a possibility, particularly because the leading term in the tree level approximation is zeta 3, and that doesn't factorize. So if this is true, actually what you immediately get that delta of G0 is proportional to G0, and the solution when regularized turns out to be G0 is the E3/2 Eisenstein series of M. I mean, this is the analog of this expression, which I'm not going to write down. But this apart from Dean-Stanton's also has contributions from the string world sheet wrapping around the T2. So it's also world sheet Dean-Stanton contributions. And when you actually add the R to the 4 contribution here, remember the R to the 4th term actually has 0 U1 charge, 0 SU2 also. So it is the only contribution which can receive, only interaction which can receive contributions both from the SL2 moduli and the SL3 moduli. So from what I told you earlier, from the SL2 it involves E1 EU hat. This is the first Eisenstein series, and for this one is this contribution, and the relative coefficients are fixed because this one at the one loop level exactly has E1 of TT bar, and you know that this answer must be symmetric under interchange of T and U. because it's the R to the 4 multiplet, and when you go from type 2A to type 2B, which interchanges a Kähler and complex structure, things must be the same. So this actually also tells you how this R to the 4 term arises. So what I've told you is very schematic, and of course, there are many things that can be done, because I've told you in a very specific set of couplings in a very specific theory. And so in general, constructing effective action even for maximally supersymmetric theories is difficult. There has been conjectures for these guys at lower dimensions by Green, Van Hove, Miller, Rousseau, and others. And clearly a lot remains to be done. So I'll end here.
I missed, so what was the argument that you don't get the second term, that lambda 2 was 0? Or?
This is not an argument. This is what I got from supersymmetry, and I of course did not calculate the coefficients. Yes. So the point is, in literature, essentially you hear the statement that G0 is given by the Eisenstein series of SL3Z. Yes. This is what Kritz's P. originally conjectured. But this would seem to be at odds with that. However, it could very well be that this itself being a modular form of weight 0 is actually proportional to G0 itself. Or it could be that lambda 2 is equal to 0.
Because you said something that the first constant term doesn't factorize.
Which one? Exactly. So the reason I was telling, because remember in 10 dimension you had an equation where you have something like this, and the source term was E3 half square. Yes. And the important thing is E3 half actually had a zeta 3. So that is a zeta 3 square which factorized into E3 halves. But here the leading term itself is just zeta 3. So it doesn't factorize.
I was thinking maybe it could be some cusp form or something that doesn't have any constant term.
I guess that's true, but yeah, that could very well be the case. So in other words, that must have then only non-perturbative contributions. Yeah, because at genus 0 and 1 you know the answers basically.
Because I think that would be very interesting, because mathematicians don't really know
exactly
how to construct them. So
exactly.
Really
also there's no explicit expression for them anyway. For example, yeah. So it could be exactly. So using supersymmetry, this is what I got. This is what I found a little bit striking, that even for the R to the 4 multiplet, you're getting a Poisson equation and not a Laplace equation. And with the source terms which are given by interactions in the same supermultiplet. This is what I found interesting. And I think I tried to kind of understand schematically how these kind of things would also work for n equals 8 and d equals 4. So they basically have these original papers by Howe, Stelly, and Townsend et al., where they construct the superfield. So the lowest component actually has this phi, ij, kl, which is in the 70 of SU8 and so on. Then you have the spin halves which are in the 56 of SU8. So you can do the exactly analogous construction, and I think you'll get the similar kind of answer. And essentially it has to do with the fact that for this G mod H, coset H is non-abelian.
Questions? I can ask a somewhat general one. If you ignore instant ones, you still have perturbative contributions to all these things. And they usually seem to be genus 0 and 1 or 2, sometimes 0 and 2, or 0 and 3 also.
Up to 3, yeah.
Do you understand why a priori, or it just happens?
Well, yes, there are some non-renumeration theorems due to Berkowitz. That essentially he proved that up to what is surely known is up for d to the 6 r to the 4. D to the 2k r to the 4. This is contributions only up to genus k. So this is not true for k equals 0. There is up to genus 1. But that you know, because r to the 4 is protected by anomalies, because in 11 dimensions is given by C3 times x8, where x8 is the one obtained from descent in 12 dimensions. So up to here you know. And essentially it follows by the lambda 0 mode counting in the Peirce spinor form.
Up to genus k, but in principle all terms from 0 to k.
Exactly.
But in the examples you gave.
Exactly, that was a specific case. Exactly. In fact, for d to the 6 r to the 4, the genus 0 you know, that's zeta 3 square. And the genus 1 also is non-zero. So that's actually zeta 2, zeta 3. That actually follows from the equation. And genus 2 also is non. That's zeta 4, and this is zeta 6, the genus 3.
This is 8 dimensions.
This is in 10 dimensions.
10 dimensions.
Yes. So in 8 dimensions, for d to the 4, and r to the 4, and d to the 6, r to the 4, I have conjectures also. Okay. But actually this precisely works out.
So in general, all appear.
All appear, exactly. In fact, the conjectures which I had for d to the 4, r to the 4, has also been verified recently by this Green et al. When they in lower dimension then decompactify and got what I got. But the important thing is then actually this turns out to be much nicer. For example, here instead of just numbers, these are actually modular forms of the SL2 for itself. So for example, you get things like, something like E2 UU bar plus E1 UU bar, E1 TT bar plus E2 TT bar and stuff. So it's very nice. This one loop amplitude gives you something manifestly symmetric in the complex and Kähler moduli, and they're itself modular forms of certain weight of SL2 times SL3.
Berkowitz and Waffa, they had a different approach to calculating some hybrid with
Yes,
eight dimensions.
yes, exactly.
n equal to 4 topological.
So they basically have stuff like, you see, h to the 4g minus 4 r to the 4, right?
So
And
could
then-
one somehow
Yes,
analyze those
I'll-
terms with your...
Yeah, I'll just make a comment. So they basically did it in 8 dimensions, and also they decompacted it into 10 dimensions.
Yeah.
And actually, what they obtained was essentially roughly for d to the 2g r to the 4. This would be something like, I forget, so something like g plus half or stuff, something like that. But that is not correct. Because I think the main problem is there's one issue which didn't come up at all in what I told you, is that there are infinite divergences in these terms. And it's precisely from d to the 8 r to the 4 this comes up. And because of that, these just don't work anymore. So in fact, it's believed that d to the 8 r to the 4 will receive contributions from all genus and not just two genera.
Okay. Thank Anirban again.